Hello students, today we are going to discuss about crystallography. We find this topic in solid state physics. First 40 minutes are allotted for the brief presentation of the subject, and last 20 minutes are allotted for your clarification of doubts. You can call us at 040-2703-1431, 2703-1432, 2703-1433. I repeat once again, you can clarify your doubts by calling us at 040-2703-1431, 2703-1432, 2703-1433. Today we have Professor Lakshmipathi, Professor and former Head Department of Physics and presently Chairman Board of Studies. He is working for the last 30 years in Osmania University. He has occupied various positions in the university. He has published nearly 30 papers in national and international journals. He has produced one PhD. He has done lot of research in solid state physics. Professor Rao is with us in our studios to clarify your doubts and as a subject expert. A crystal is a solid made up of atoms arranged periodically in 3 dimensions. Generally, solids occur in 3 types: amorphous, polycrystalline and single crystal. Many important properties of materials such as mechanical, thermal, electrical and magnetic are found to depend upon the crystal structure and electron states within the crystal. In crystal physics, we explain the macroscopic properties of the crystal in terms of microscopic properties of the particle with which the solid is made up of. The study of geometric form and properties of crystal using X-ray diffraction, electron diffraction, neutron diffraction. But today we will confirm only the geometrical structures of the crystals. So, Professor, how can we explain the lattice, basis and crystal structure for our students?
So, before actually giving the explanation for lattice, basis and crystals, I would like to briefly touch upon what is crystallography. And the word crystal came from the Greek word crystallus, meaning clear ice. And you can see in these slides some of these crystal flakes, and which originally they called them as crystals. And crystallography is the science of crystals, and one must know what a crystal is before studying crystallography. And as you rightly pointed out, you have crystals in different forms, polycrystalline materials and single crystals, and another state is amorphous. And in a given solid, if the atoms, molecules or ions arranged periodically in 3 dimensions throughout the solid without any break, then we call it as a single crystal. On the other hand, if in a solid, though the periodicity exists, this periodicity is broken at certain regions, and these are called as polycrystalline materials. And in polycrystalline materials, it is an aggregate of single crystals, so that each region here is called as a grain, and each grain you can call it as a single crystal, so that polycrystalline material is the aggregate of single crystals. And if there is no periodicity, if it is broken from one point to the other point, then we call it as amorphous. So, we do not expect any periodicity in amorphous materials. And coming to your question, we should know what is the language of crystals. and you asked what is the difference between the lattice, basis and crystal structure. And crystal structure or crystal is a physical concept, whereas lattice and lattice points, it is a mathematical concept. So, if you imagine a set of imaginary points which are connected by certain mathematical relation, which is given by t is equal to n1a plus n2b plus n3c. So, then all these lattice points put together, they form a lattice, and these points starting from one lattice point, we can go to any other lattice point by considering different values for n1, n2 and n3 in the equation, and here a, b, c are the distances, the vector distances along the three crystallographic axes. So, this is basically a lattice is nothing but a collection of imaginary points which are connected by means of a mathematical relation. So, that starting from one lattice point, you can reach any other lattice point by using this mathematical relation and by giving different values to n1, n2, n3, which happens to be integers, and a, b, c are the lattice translational vectors. So, that each point is called as a lattice point in this particular lattice. So, this is the basic definition of lattice and lattice point. Sometimes this lattice is also called as the space lattice, because we are imagining these points, a set of points in three dimensional space. So, that is why it is also called as a space lattice. And I told you that it is only a mathematical concept. Then we must establish a relation between the mathematical concept and the physical entity, which is a crystal. So, here in a crystal or a solid, it consists of either molecules or ions or atoms. For example, you take this. This is a molecule. This is a water molecule. If you imagine an ice crystal, it consists of these molecules at each of the lattice point. So, that starting from one lattice point, I can translate this along the three dimensions by using the equation t is equal to n1a plus n2b plus n3c, and so that all the lattice points, they are occupied by this H2O molecule. So, that this is called as the basis. For example, instead of this particular basis, I can show you some other basis. So, this is an NH3 molecule, ammonia molecule. So, that in ammonia solid, you have this unit which is repeating at each of the lattice point. So, this is called as the unit that is repeating is called as the basis, and whereas the points that we are identifying in the lattice is called as the lattice point. So, that with each of the lattice point, we associate this particular basis. Then the lattice is converted into a crystal. So, crystal is a physical concept, this is a sheer mathematical concept. So, we are converting the lattice into the crystal structure by associating with each of the lattice point a basis. So, if you associate a water molecule, that lattice will be converted into crystal, this ice crystal, whereas if you associate this NH3 molecule, it will be converted into an ammonia solid. So, like that any solid, for example, if it is an atomic solid, your basis will be one atom. For example, you take sodium crystal, sodium atom will be the basis, and with each of the lattice point, I can associate this particular basis to convert that into a crystal. And here we should understand the language of the crystals also, because we have International Union of Crystallographers who refer to all the properties, and you should have a common language, so that all the scientists working in this field can understand each other. For that, you should know what is the language of crystals. Now, having understood what a lattice is, so a lattice can be imagined as being translated by a particular unit cell. You imagine a wall. How do you construct a wall? You take a brick and put the brick side by side, and similarly in this direction also, and we construct the whole wall. So, the starting point or the unit with which we are constructing the wall is the brick. Similarly, here a unit cell refers or represents a particular lattice. so that each lattice will have a particular type of unit cell. It is characterized by a unit cell, and in sometimes the same lattice can be imagined, or they can be imagined starting from different types of unit cells also. So, or you have to understand that there are basically two types of unit cells. One is the primitive unit cell, which is shown in this slide, and non-primitive unit cell. So, let us try to understand the difference between the primitive unit cell and non-primitive unit cell. If you look at that, in case of a primitive unit cell, you have the lattice points only at the corner of the unit cell, and whereas you have the other types of unit cells also, where you have lattice points in addition to the corners at some other points also. Those are called as non-primitive unit cell, and the contribution from all the lattice points to the unit cell, if it is 1, then we call it as a primitive unit cell. So, or in other words, a primitive unit cell will have lattice points only at the corners, and they contribute 1 lattice point to the unit cell, whereas the non-primitive unit cell, they contribute more number of lattice points to the given unit. For example, I will show you here, this is a unit cell. So, this is called as a primitive unit cell. We have only at the corners, there are no other atoms, whereas unit cells like this. So, you can see, so this is called an FCC unit cell, face centered unit cell. In this unit cell, you have lattice points at these corners and also at the centers of these faces. So, that is why we call it as face centered cubic cell. This comes under the category non-primitive unit cell, whereas this simple cube, it comes as primitive unit cell. This is the difference between the primitive unit cell and non-primitive unit cells. And as I told you, the basis is repeated continuously on the lattice, so that will be converted into the crystal structure. So, this is the answer for your question, and how to distinguish between the lattice point and crystal structure, and also the related concepts of primitive unit cell and non-primitive unit cell.
Sir, we find symmetry in the petals of the flowers and in the wings of the butterfly also. We have symmetry in the crystals, as we have seen now in the face centered cubic crystal. Shall we explain what is the symmetry that is existing in the different crystal structures?
Yes, as you pointed out, we observe in nature at many places the symmetry. In fact, nature loves symmetry. So, if you look at the human being also, for example, if I imagine a plane like this, so that means dividing the body into two parts, you can see that the left part is the mirror image of the right part. So, that if I cut like this and then put a mirror here, I can see the entire person. So, like that, even the alphabets also are having certain symmetry. So, these crystals, they are characterized by, in addition to the periodicity, the crystal symmetry. So, the symmetry, I can, for example, I can show you what symmetry is exactly by using this particular model. You look at this unit cell, and if I imagine an axis like this and rotate the crystal by some angle, you can see there is no difference in the appearance in the initial position and after the rotation is completed. So, this is called as the symmetry, it possesses certain symmetry. So, that means before the operation, that is rotation by 90 degrees, and after the operation it looks exactly the same. So, that means it is symmetrical around this particular axis, and similarly I can imagine another axis also like this and then rotate, so that this is the initial position and I can rotate it by some angle, so that again it gains the initial position. So, that means absolutely there is no difference between this position and the position with which we have started. So, that means this is symmetrical around this particular axis. So, that means symmetry operation means we perform certain operation on this, so that before the operation and after the operation, if the object or crystal looks exactly the same, then we call it as a symmetry operation. So, this is the basic definition of symmetry operation. and this already I have explained you, the same thing is written here. The symmetry operation will give you a symmetry element. Now, in this particular operation I am rotating it, so that the symmetry operation is rotation, and similarly you have some other operations also, and symmetry operations are basically classified into two categories. One is the translational symmetry operation and the other one is the point symmetry operation. Translational symmetry operation already I had explained you regarding the basis and translating it over all the lattice points, so that is converted into crystal structure. So, what we have done there is the translational symmetry, whereas the other type of symmetries that we have, and this is governed by T is equal to N1A plus N2B plus N3C. So, this equation corresponds to the translational operation, whereas you have other type of symmetry, that is the point symmetry. And point symmetry is, point symmetry does not involve translation, and I have shown you the water molecule. This is having particular symmetry. I can explain you the symmetry. For example, if I imagine an axis of symmetry like this and rotate it by 180 degrees. So, before the operation and after the operation it looks exactly the same. So, that means this is a symmetry operation. So, in all such symmetry operations, what happens is, there is one point which is called as the center of gravity of this particular molecule, which does not move during the operation, whereas all other points move. The center of this particular atom, the oxygen atom, it will not move or change during the operation. So, that is why we are calling all such symmetry operations which pass through a particular point in the molecule or the unit cell, and which the point will not change during the operation. These are called as point symmetry operations, or in other words, all the point symmetry operations, they pass through a particular point in the crystal. So, translation operation, it corresponds to the crystal, so that we can translate it along a plane, and then whereas the point symmetry, it is confined to a particular point. Same is the case even with respect to the NH3 molecule, which I have shown you. There also the N, the atom N will not change, the central point of that will not change during the point symmetry operation. So, these are the types of symmetry operations that we have, and these point symmetry operations, because here you can, I have shown you this particular first rotation. In addition to rotation, you have other point symmetry operations also. In fact, there are 5 different types of symmetry, point symmetry operations. They are rotation, reflection, inversion, improper rotation, and then identity. I can show you the examples for these things. So, here the rotation, the day to day example, all the students are familiar, all of us are familiar with the playing cards. For example, you take, I have shown you here spade 2. In spade 2, it has certain symmetry. So, if I imagine an axis perpendicular to this particular playing card and rotate it by 180 degrees, then before the rotation and after the rotation it looks like exactly the same. And similarly, here I have shown you that if I rotate it by 90 degrees, it remains the same. Whereas, in this case I have shown you another axis of symmetry. This is called as a threefold symmetry axis, whereas we have to rotate it by 120 degrees to get back the initial position. So, that means depending upon the type of the unit cell or the type of the molecule, for example, NH3 you can take. Easily you can understand here, this NH3 molecule, if I rotate by 120 degrees, then it looks like exactly the same. Whereas, the molecule, the water molecule, if I rotate by 180 degrees, it looks exactly the same. So, that means though the nature of the symmetry operation is same, that is the axis of rotation, but the amount of rotation is different in different types of molecules. So, that means you can have angle of rotation as 90, 120 or 60, 180, and corresponding to these rotations we call them as n is equal to, n means a rotation axis. It is represented by the symbol n. So, here in this slide you can see n is equal to 1, 2, 3, 4 and 6. N can take the values 1, 2, 3, 4 and 6. 1 means 360 degrees. We have to rotate by 360. 2 means 180 degrees. So, if the total amount of rotation is 360 degrees, all objects remain exactly the same. So, if I rotate it by 360 degrees, then we call it as n is equal to 1. Whereas, if I rotate by 180 degrees, so 360 by 180 I get 2. So, that means in one full rotation 2 times it will have the same position, it will be identical. So, that is why this called as n is equal to 2, or the axis of symmetry here is given as diad axis, also it is called as n is equal to 2, whereas here you have n is equal to 3 because the amount of rotation is 120, whereas for the cube I have shown you it is 90 degrees I am rotating, so it is 4. So, if you have the hexagon, then we have to rotate it by 60 degrees, that is called as n is equal to 6. So, that means you can have n values as 1, 2, 3, 4 and 6, but not 5. So, because the reason for this is 5, a polygon having 5 sides, because all the crystals should satisfy not only the point symmetry operations, but also the translational symmetry. So, translational symmetry means I am translating, so that when I translate a unit cell, the whole space must be filled up without leaving any gap in between. Whereas, if you take a 5-fold polygon and in 2 dimensions, if you translate it, you can see that these polygons, they are not filling up the gap completely and there are some empty spaces in between. So, because of these empty spaces, we say that it is not a crystalline arrangement. So, if it is a crystalline arrangement, when I translate the unit cell, there should not be any gap in between and the whole space must be filled up totally. Then only we call that as a unit cell. So, because this property is not satisfied, we cannot have an axis of symmetry with a value n is equal to 5. So, this is regarding the axis of symmetry. Next comes the reflection. Already I have given the human being example. So, in the chart you are seeing a dog. There, if I draw a line, then the left portion is the mirror image of the right portion. So, that even if you have only half of that portion and if I keep a mirror along that, you can see the entire image, it gets reflected. So, that is called as the reflection plane. For example, I will show you here with respect to this particular unit cell, I can show you that. So, here you have a cube, in my hand you have a cube and you can have or you can explain the plane of symmetry with respect to that. For example, if I have a plane like this, the left portion is the mirror image of the right. For example, you can see this, I am separating that. So, that if I have only half of this also, if I put a mirror here, the entire cube can be seen. That is why it is called as a mirror plane, plane of symmetry. And similarly, I can have another plane like this also. So, in addition to these two planes, there is another type of plane also. Take this cube, we have shown you these vertical planes. In addition to the vertical planes, you also can have a diagonal plane. So, a diagonal plane means diagonally I can separate out these two. So, you can see here the diagonals are being separated. So, this half will be reflected into the other half. So, this is called as the mirror plane. So, in this you can have even horizontal plane also, vertical plane, horizontal plane and then the diagonal plane. These are the 3 different types of planes of symmetry that you have in these crystals. So, in addition to these two, the third one, it is inversion. So, inversion is nothing but rotation, already we have seen, followed by inverting it at a particular point. Inverting means reflection at a point. Earlier what we have considered is reflection in a plane, but now here you can see, for example, this has a, or the next slide I will show you, you have this improper rotation or rotation inversion. So, in this case rotation followed by reflection at a particular point, not in a plane. This is called as the inversion axis of symmetry. Just like you have a normal axis of symmetry 1, 2, 3, 4 and 6, you can have inversion axis of symmetry also. They are called as 1 bar, 2 bar, 3 bar, 4 bar and 6 bar. 4 bar means rotation by 90 degrees followed by reflection at a point, that is called as the inversion. So, rotation, improper rotation or rotation followed by inversion. Inversion means, for example, if I have a point here, I will have another point here. So, this is nothing but reflecting at the center of the cube. So, rotation followed by inverting it through the center is called the inversion symmetry. So, for example, this object, it is not having a simple reflection or simple rotation, but if we combine these two, it will have the combination of rotation followed by reflection at a point, or this is called as the inversion symmetry. So, these are the examples for the inversion symmetry, and then finally the identity. So, identity, all objects possess this particular symmetry. Identity means rotation by 360 degrees or doing nothing operation. So, that means any object you take it, and if I rotate by 360 degrees, it remains the same. So, then you may ask, why should we have this particular symmetry at all? So, for calculating or for having some mathematical calculation, we require, for defining the point groups also, we take the help of this particular symmetry operation, which is called as the identity symmetry operation. So, these are the 5 different point symmetry operations that you have.
Sir, shall we explain point groups and space groups?
Yes, coming to this is a very important concept, the point group and space group. Ultimately, the structure of any crystal is given by its space group. So, you should know what a space group is. So, if a space group is to be understood, then first we must understand what a point group is. So, again I will take this particular example of this molecule, water molecule, and this water molecule, it has an axis of symmetry. This is the twofold axis of symmetry, n is equal to 2. In addition to this, it also has the reflection planes of symmetry. For example, I can imagine a plane of symmetry like this, so that this ion is reflected into this, half of this is reflected into the other half. So, that means you have a mirror plane like this, and similarly you can imagine a plane like this also, so that half of this is reflected into this, half of this is reflected into this, half of the third molecule ion also is reflected into this. So, that means if you take a water molecule, it has an axis of symmetry which is called as n is equal to 2, and plane of symmetry, 2 planes it has, one plane like this, one plane like this. All these planes and also this, they are passing through one particular point here. So, this is center of gravity of the molecule, and that center of gravity remains unchanged when we perform these operations of axis of symmetry and plane of symmetry.
Sir, shall we break for news? Welcome students to the live teleconference. I repeat the phone numbers, you can clarify your doubts: 040-2703-1431, 2703-1432, 2703-1433. Professor, we will continue with the discussion point group and space groups.
I was explaining the point groups. So, point groups are basically related to either molecules or the unit cells. So, that means we are discussing about the symmetry around a particular point, and a given molecule can have more than one point symmetry operations. For example, this water molecule, as I told you, it will have n is equal to 2, this is the axis, n is equal to 2, plus it has 2 mirror planes, so that if you combine all the symmetries passing through a particular point, then we get the point group. So, that means all the combination of all the point symmetry elements passing through a particular point, either in a molecule or in a unit cell. Even in a unit cell also, you will have n is equal to 3 axis, n is equal to 4 axis here, and also you have n is equal to 2 axis passing through this, and you have mirror plane, vertical planes to vertical plane, and another horizontal plane and diagonal plane. So, all the symmetry operations are passing through a particular point, that is the center of the cube, which happens to be the center of gravity. So, we have to collect all the symmetry elements passing through a particular point. So, this is called, that means we are formulating a group, a mathematical group, combination of all the symmetry elements passing through a particular point is called as a point group symmetry. So, the difference between point symmetry and point group is point symmetry is an individual symmetry operation, like it can be an axis of rotation, it is a plane of reflection or inversion or identity. So, these are the different point symmetry elements we have, whereas point group is a combination of this. That means you can have an axis of symmetry, certain planes of reflection, and also more than one axis of symmetry also it can have. So, if a molecule possesses more than one, and similarly if a unit cell possesses more than one symmetry elements, we club them into a group, a mathematical group, which is using the group theory principles. We work out how many point groups are there like this in 3 dimensions. So, here by working out what are all the possible, what molecules you have, what unit cells you have, if you combine them, then these point symmetry elements, that is n is equal to 1, 2, 3, 4 and 6, and also m the plane of reflection, and bar 1, bar 2, bar 3, bar 4, bar inversion. 6, and also the inversion symmetry and the other symmetries, they can be clubbed into different point groups. So, that if you have the mathematical relations and it has to satisfy the group theory rules applicable for any mathematical group. A group is nothing but a collection of the similarly situated elements. It could be the marks obtained by a candidate. For example, there are 40 candidates in a class. If you collect all the marks, that forms a mathematical group. And similarly, if you have 40 girls in a class, identical elements combined, it is called as a group. The same principles of mathematical group are applicable to the point groups also. Here we are taking the combination of all the point symmetry elements passing through a particular point, either in a molecule or in a unit cell, so that you can formulate a point group. So, if you do in 3 dimensions, you have 32 number of point groups all put together. So, that means we must consider different types of combinations of this, which will give rise to 32 point groups. And a point group requires, now comes, okay, there is another concept, that is Bravais lattice and crystal system, which is related to this particular point group. Then a point group requires a particular type of arrangement of lattice points in space. So, when we said it is a water molecule has a particular type of symmetry, and similarly.
Sir, shall we break for a phone? Phone is ready.
Yes.
Hello.
నమస్కారం అండి.
చెప్పండి
మేడం. సార్ నమస్కారం సార్, ప్రొఫెసర్ గారు
చెప్పండి. నమస్కారం చెప్పండి.
You are telling for this by dividing each and every.
Sir, we will continue with the discussion.
Yes.
హలో కొంచెం మెల్లిగా మాట్లాడండి, మీ టీవీ సౌండ్ తగ్గించండి, మాకు ఇది వస్తుంది, డిస్టర్బెన్స్ వస్తుంది. చెప్పండి మీ డౌట్ ఏంటో చెప్పండి. We are not discussing about the defects in the crystal lattice, isn't it? We are discussing about the crystal structure. We will continue, we will clarify your doubt, but in a different occasion we will discuss in length, but now we will briefly discuss, sir.
No, you have understood what a crystal is. A crystal is nothing but the periodic arrangement of atoms or ions or molecules in a solid. If there is any deviation from this periodic arrangement, then we call it as a crystal defect. So, any deviations in the periodic arrangements, they are called as crystal defects or lattice defects. I hope this clarifies your doubt. So, coming back to this point group, a point group requires a particular type of arrangement. For example, you take the same example of water molecule I am taking, it has certain arrangement of atoms. So, when I translate, then you need a particular type of arrangement of lattice points in space. Similarly, NH3, it needs a different type of arrangement, because whatever symmetry is possessed by this particular molecule, it should be translated at all the lattice points also. So that you need these 32 point groups, like this is one point group, it belongs to one point group, this belongs to another point group. Similarly, if you take a cube belongs to a different type of point groups. So out of the 32, you have, these are the 3 different point groups. So these 32 point
Sir, we
groups.
are getting a phone call. We will take them.
Okay, we will break. Yes.
Hello? Hello?
Hello.
Cheppandi.
Hello. If you keep some weight on that crystal, how it will share on that cubic crystal? Clarify the matter, madam.
Please repeat.
Could you
your
please
question.
repeat your question? Weight.
No, if you keep some weight on one crystal,
Wait.
the crystal, how it will share on the points?
No, I have not understood your question.
No, if you keep some weight on the crystal, how the shape will change, or he is telling?
No, if it is subjected to some force, there are some properties will change. So there will be distortions in the lattice, there will be distortions in the crystal structure if it is subjected to certain pressure. So what if I have followed correctly, you are asking me, if I apply some pressure on these crystals, what happens to the crystal structure? The crystal structures also change, because the lattice parameters A, B, C in the 3 different directions, they also keep changing. So if it is subjected to pressure, the crystal structure changes. Yes.
And the pressure should be of higher order.
Yes, yes.
Not normal pressure. We will continue.
Okay. Now these 32 point groups, they require a different number of arrangement of lattice points in space. So these 32 point groups require 14 independent types of arrangement of lattice points in space. So these are called as the Bravais lattices. 14 Bravais lattices are required to explain the 32 point groups. So a Bravais lattice means it can be understood by means of a unit cell. So each lattice can be understood by means of a unit cell. So you need 14 different types of
Unit cells.
Bravais lattices for understanding, or for as a requirement of the 32 point groups. So these 14 space lattices are called as Bravais lattices, and these Bravais lattice, each Bravais lattice is defined by 3 axial lengths. For example, you take this. If you take this particular cube, it has 3 axes, 1, 2 and 3, x axis, y axis and z axis. So that it is characterized by the 3 crystallographic axes and the angles subtended between these 2. So if you call this as A axis, B axis and C axis, the angle opposite to the side A is called as the angle alpha. Similarly, opposite to B is called as beta, and opposite to C is called as gamma. So each unit cell is characterized by A, B, C values and alpha, beta, gamma, the angles subtended by these angles. So these are called as the characteristics of these unit cells. So that these 14 independent ways of arranging lattice points will have 14 different unit cells, and each unit cell is characterized by A, B, C value and alpha, beta, gamma. So that these 14 Bravais lattices will have different values for this A, B, C and alpha, beta, gamma. So depending upon these values A, B, C and alpha, beta, gamma, these 14 Bravais lattices are clubbed into 7 crystal systems. So this is the relation between the crystal system and the Bravais lattice. Based on the angular relationships and the axial relationships, they are clubbed into 14, and these are the 14 Bravais lattices that you have. So that means these 14 Bravais lattices are clubbed into 7 crystal systems. That means one particular crystal system will have more than one Bravais lattice. For example, you take cubic. In cubic, you have more than one Bravais lattice associated with this. You have a simple cubic, you have face centered cubic. This is the face centered cubic, and also body centered cubic also you will have. So now you might have noticed the difference between each of the unit cell. So though it has a cubic, simple cube, this is called as a primitive or simple cube, where the atoms are there only at the corners, and this is the face centered cubic unit cell. And you also have a body centered. In a body centered, what you have is the atoms at the corners, and at the center of the body you have another atom, that is called as the body centered one. So, all these things, the axial relationship and the angular relationships are same, but they have different Bravais lattices. So, that is why these Bravais lattices are clubbed into one crystal system, and we call it as a cubic system. So, like this you have 7 crystal systems, which I can show you here. The crystal system is shown here, and then the first triclinic. In triclinic you have only one unit cell, so that is primitive, whereas for monoclinic you have 2 unit cells. So, one is primitive, one is C lattice. C lattice means C centered, only one pair of faces, that means opposite faces are centered, not all the faces, that is called as C centered lattice, a primitive lattice and C centered lattice. And like that, orthorhombic will have 5 unit cells, primitive, C centered, and I means I and F. I is the body centered and F is the face centered, and all these they can be clubbed into one orthorhombic, because these 4 will have the same axial and angular relationships, that is A is not equal to B not equal to C, and then alpha is equal to beta is equal to gamma is equal to 90. Those are the characteristics of the orthorhombic system. So, in the slide that is shown there, the first column it gives you the crystal system to which it belongs to, and then how many unit cells are there. So, P, C, I, F in case of orthorhombic, and all these unit cells will have the same axial and angular relationships, and what are the point groups associated with this particular crystal system are also listed there in the last column. So, that if you look at the last column, if you concentrate in the point groups, for triclinic system you have 2 point groups, monoclinic you have 3, orthorhombic you have 3, tetragonal you have 7, triagonal 5, hexagonal 7, and cubic 5. So, these all, if you add up all these point groups, they come to 32. So, that these 5, for example, cubic, just now I have shown you this example, primitive, body centered and face centered. They belong to the cubic class, where A is equal to B is equal to C, and alpha is equal to beta is equal to gamma is equal to 90 degrees, and there are 5 point groups here. A particular type of notation is used here for representing the point groups. Already you are familiar with this notation, because 1, 2, these numbers, they represent the axis of symmetry. M represents the plane of symmetry, and if you write here, for example, you take the tetragonal system. In tetragonal system it is written as the third point group is 4 by M. 4 by M means the plane that is there, the reflection plane is perpendicular to the axis of symmetry 4. On the other hand, if I write only M3 or MM2, those are also figured here, these are the parallel planes. If it is a perpendicular plane, we write it by M. If it is a parallel plane, we write it by the side of that. And similarly, 1 bar, 2 bar, 3 bar, 4 bar and 6 bar, they represent axis of inversion axis of symmetry. So, that the combination of this, for example, I will explain you one particular point group, it is a 2 by M. So, that means 2 by M point group, it consists of a dyad axis of symmetry and a plane of symmetry perpendicular to that. So, combination of these two is called as point group 2 by M. And similarly, you can explain all other point groups like this 4, 2, 2. So, that means it has more number of axes of symmetries, not only 4, n is equal to 4, it has n is equal to 2 also. And similarly, bar 3M, bar 3 corresponds to inversion axis, and also it has a mirror plane. So, these are all the various point groups you have, which number to 32 in 3 dimensions. And coming to the space groups. Now, here we are not associating the point group with the Bravais lattice to which it is attached to, whereas you can associate each point group. For example, in a crystal system you have 2 by M, and that corresponds to you have P and C, 2 unit cells. So, this 2 by M can be attached to P and as well also C. And similarly, the 5 point groups that you have in cubic case, they can be associated with simple cube, they can be associated with face centered cube, and also associated with body centered cube. So, that means what happens, the 5 point groups that you have seen, they are associated with the simple, and then a body centered 5 plus 5, and also face centered another 5. That means they get multiplied in number, and altogether you will have 15 in number, 5 with primitive, 5 with face centered, 5 with body centered. So that these are, when we associate the point groups with the relevant body, the body centered unit cell or FCC or simple cube, they are converted into space groups. So in case of space groups, the difference between point groups and space group is, in space groups we study the symmetry of the particular space, spatial atoms, how all the atoms are arranged in space and what is the symmetry around the atom, all the atoms. Whereas in point groups we study only the symmetries around a particular point, that is the center of gravity of the molecule. We confine to molecules or only unit cell, not to crystals. So when you add the translational symmetry to the point group, then also we get additional symmetry elements. So like this, what happens is, we can club these point groups with the relevant lattice, and also there are some additional symmetry elements which are called as glide plane and screw axis, and so that if we club all these things, they will be converted into space groups which are 230 in number. So basically this is the difference between point groups and space groups. Yes.
We can continue furthermore.
Yes.
We can explain, because what is Symmorphic and Symmorphic?
The Symmorphic space groups are when you associate the point groups with the relevant lattice, it gives rise to 73 space groups. So these are called as the Symmorphic space groups. So here I have shown you what the Symmorphic space groups are. A straightforward application of these 32 point groups to the corresponding unit cells, it will give rise to 73 space groups which are called as Symmorphic. Non-Symmorphic space groups include additional symmetry elements which we have not considered so far. So these are two additional symmetry elements are called as glide plane and screw axis. These two symmetry elements, so here I can show you the example of, so you can see here, I hope you are seeing this. These atoms are arranged, and the symmetry exhibited by this is a threefold axis of symmetry. This is the normal axis of symmetry. Whereas if the atoms are arranged in a different way, you can see this, it is not a simple threefold, rotation followed by a translation by some distance, and again rotation followed by another translation, and rotation followed by another translation, you have the atoms. So the atoms are arranged like this, and this is different from the normal threefold axis of symmetry. And if you look at these atoms, you feel as if I join this with a line, you feel as if you are moving along the thread of a screw. So that's why this axis of symmetry is called as screw axis. And similarly, coming to the glide plane, if it is a normal glide plane, what happens? Every atom is reflected into the other atom. Whereas if it is a glide plane, you have reflection followed by translation, and again reflection followed by another translation, you will get another atom. So it is a combined symmetry element or compound symmetry elements. So these two compound symmetry elements have also to be taken into consideration, so that if you take the glide plane and this particular screw axis, you get another 157 space groups, so that 73 Symmorphic, 157 non-Symmorphic space groups, both put together, you will have 230 space groups in all.
Sir, briefly can we tell different cubic structures? Briefly we will go through.
Structures, you have different crystal structures. The crystal structure can be understood by means of the Bravais lattice first, what Bravais lattice, and also the basis that is to be associated. So for example, you take a simple cube, and for a simple cube you can associate different types of bases. Depending upon the basis, the structure transforms into either CSCL structure or NaCl structure or FCC, BCC, and there are so many cubic structures that you have. Basically you have the, if you want to understand the crystal structure, first you should understand what is the corresponding Bravais lattice, and then, so I will here briefly show you the crystal structures. So this is the crystal structure, a simple cubic crystal structure where the Bravais lattice is primitive and basis is one atom, and then this is the body centered cubic crystal. And in a body centered cubic crystal, you have not only at the corners but also at the center of the body, and then you have CSCL structure. The difference between body centered and CSCl is, in body centers all atoms are identical, and whereas in CSCl you have two different types of ions. And finally, I will just show you the FCC structure. This is the FCC structure, and these are some of the important cubic structures that you can have.
Thank you, Professor, for your cooperation and detailed explanation of the crystallography geometry structures, different crystal structures. Thank you.
Thank you.